starting approximately this time, depending on when the chair seminar is complete. Do you guys have your first meeting on Friday? Those of you who were in that seminar? Starts at 9:30?
Starts at 9.
Starts at 9?
Yeah.
Did it finish well before 10:30?
I think it was like right at 10:30.
All right, so right at 10:30, we'll get started here. All right, so the problem set is a long one, so I hope you're getting going on it. And it's due a week from today. I wanted to discuss administratively the issue of the problem session, if it's at a good time, and try to accommodate everyone, because I know some of you can't make it. Unless I was making, no one was there yesterday. So that's fine with me, but it's if you guys would like some FaceTime, as we say, then I'm available for that. So I'm going to poll everyone again. I didn't get very much response last time about when would be good times, and we'll try to figure it out. Okay. Anybody have any administrative issues? People trying to have people been able to access the materials on the web, or any issues relating to that? Everything doing okay? All right. All right. So let's get started with the work at hand. The last section we were reviewing the study of more detailed description of the atomic structure in hydrogen in particular, in the including relativistic corrections. Relative corrections aren't big in hydrogen, but they're not completely negligible either. And we characterized sort of get a feel for how big relativistic corrections would be by just looking at the fundamental constants, and from that deducing what the characteristic speed of the electron is in hydrogen. And that characteristic speed in units of the speed of light is called the fine structure constant, alpha. Okay? And it's approximately 1 over 137. So with that, we wanted to look at relativistic corrections. And one way to go about that is to start with a relativistic description in quantum mechanics, which involves the coupling of the particle to its antiparticle in any relativistic description. And so the description of the electron involves also the positron, the anti-electron, and that is the Dirac equation. Now that itself, as we discussed, is not really even the full description, because it does not involve the quantized vacuum of the electromagnetic field, which would dress the electron and the positron as well. I just wanted to write this down again because I was so silly last time and wrote down this matrix backwards, because I looked at this and my notes were just wrong. Because it has to be that way. That's also corrected on the web now, so if you download the notes, they're right. And one can then go through a procedure by which one eliminates the positron wave function as a function of the electron, plugs that back in, and gets a non-local equation for the electron. And when one does that to lowest order, in the fine structure constant, one sees the Hamiltonian being a zeroth order Hamiltonian involving the standard hydrogen Hamiltonian with the Coulomb potential, and then relativistic corrections of order alpha squared, as we argued they must be. And those terms written here as we derived last time, the terms of order alpha squared are here. So the first term arose from the correction to the kinetic energy due to relativistic mass. That's one term. There's a term here that we said we didn't really derive it in any way, we just wrote it down. And this is a term that comes from the Zitterbewegung that's familiar in the Dirac equation, the fast jittering motion of the electron, which is really the fact that the electron and positron are coupled together. And this is the lowest order correction to that Zitterbewegung. And that gives rise to what's called the Darwin term. It's not the Lagrangian. And then there's a term that's the most important term, not in terms of magnitude, but in terms of beyond hydrogen, as we'll discuss at some point, the spin-orbit coupling. And the spin-orbit coupling, as we discussed, could be understood as the first, as a magnetic effect. And generally speaking, magnetic effects are down in magnitude relative to electric effects, if you have moving charges, by a factor having to do with the speed of the moving charges. Okay? So that's why this comes in relation to the fine structure constant. If I have two charges that are moving relative to one another, they're going to feel forces that are both electrostatic and magneto. Not static, but magneto, not radiation. And those forces, the magnetic forces, are down relative to electric forces by something related to the speed of the charges, because the Lorentz force is down by an order of V over C, and the strength of the field is down by an order of V over C. So the overall force is down by an order of V squared. Okay, so we understood the spin-orbit coupling physically as the coupling of the magnetic moment of the electron due to its spin. So because the electron is a charged particle with spin, it has a magnetic moment. And that magnetic moment interacts with the magnetic field due to the proton. So in the rest frame of the electron, the protons moving around it creates a current, and that current creates a magnetic field, and that magnetic field then interacts locally with the magnetic moment intrinsic to the electron. Okay, so it's a coupling of the spin of the electron to the orbital motion of the electron and proton relative to one another. Okay? And so this depended on the spin of the electron, and this depended on the orbital motion of the electron and proton relative to one another, and that's where the L dot S comes from. And the V here this is traditionally how it's written, because this is the kind of coupling you would get in other atoms, which might not have a pure 1 over R Coulomb potential because of the effect of many electrons. But in the context of hydrogen, the potential energy is minus E squared over R. It's a Coulomb potential energy. And so 1 over R, or in the atomic units, we'll just write it like this. And so this is equal to 1 over R. Yes?
Why did you have to take the same term for the spin of the proton and the magnetic field that it's from the other?
Indeed we do. and we'll talk about that maybe at the end of this lecture or maybe next time. That is a term that's reduced by a factor of the ratio of the magnetic moment of the proton to the magnetic moment of the electron. And that depends on the ratio of the masses of the proton to the mass of the electron. And so that's down by a factor of about 2,000, and that gives rise to what we call hyperfine structure. So Jen, we'll talk about that more at the end of this lecture. We'll see where we get. But there is a term here that is also the spin of the proton coupled to the magnetic field of the electron. That term is there. So we'll talk more about that in a little bit. So it's just a much smaller effect because of the size of the magnetic moment of the proton. All right?
Oh, I don't understand it because you talked the relative speed to the two particles to each other.
Yes.
And I mean, this is the same for both. They have the same spin.
No, they have the same spin, but not the same magnetic moment. So the magnetic moment, let's just do a little aside here. The magnetic moment of the electron goes like the Bohr magneton. That's what we got in our first problem set. And that's okay. Whereas the magnetic moment of the proton is proportional to what's called the nuclear magneton.
Okay, I didn't know that.
So the issue is the charge to mass ratio. If you have a given charge with a given angular momentum, the magnetic moment is different. If I thought about this as classically, I think about a spinning ball of charge. The magnetic moment depends on the charge to mass ratio. So the charge is the same, the angular momentum is the same, but the mass is different. And so the magnetic moment is different. And this ratio is about 2,000. All right, but we'll come back to that. All right, so what we wanted to do here now, what we were working on at the end of last lecture was now finding the new energy levels of the system according to perturbation theory. The ground state of hydrogen is shifted by some small amount. There is no contribution to the spin-orbit coupling in the ground state because L is 0. So there's no orbital effect in the ground state. So there's just some, overall shift, and it's whatever, some small fraction, some gigahertz. It's not interesting. It doesn't do anything. It shifts the energy in some small way. Much more interesting is what happens in, say, the first excited state. And as we discussed, and let's just go back now. So let's look at perturbation theory. Our 0th order Hamiltonian in atomic units is here, and we have our 0th order, our energy levels with degeneracy two n squared. This factor of 2 is for spin up, down of the electron. And the 0th order states involve the orbitals that we have talked about today, now together with the spin up and spin down. But of course, the magnitude of the spin is fixed at 1/2, and m sub s is plus or minus 1/2. So we have this degeneracy, so we have to do degenerate perturbation theory. The ground state, as we said, is kind of boring. Let's look at the first excited state. N equals 2, and then we have L equals 1 or 0. So we have a 2s orbital with m sub L equals 0 and m sub s equals plus or minus 1/2, and a 2p orbital with m sub L equal plus minus 1 or 0 and m sub s equals plus minus 1/2. So this is 2 states, and this is 6 states, giving a total degeneracy of 8. As we discussed, for n equals 2, the degeneracy is 8. So what we want to do now, if we have to do perturbation theory, degenerate perturbation theory, is to diagonalize our perturbation Hamiltonian in this subspace, this 8-dimensional subspace. So in the basis, this 8-dimensional basis for n equals 2, my Hamiltonian is an 8x8 matrix. It's a 2x2 matrix associated with these 2 states, and it's a 3x3 matrix in this state. And there's no off-diagonal elements between these, as we'll see in a moment. So we then just need to diagonalize this. So let's look first at these blocks, and then we'll think about these off-diagonal when they're 0. So let's look at blocks with quantum numbers n, m, and then all possible n, l, and n, s.
Does the matrix have to be 2 times 2 and 6 times 6?
It does have to be that, indeed. I should say 6 by 6, sorry. 2 times 3 is 6, but that's not what's, indeed, thanks. All right, so let's first, so what do we have here? My claim is that the kinetic energy term and the Darwin term are diagonal. In this basis. How do we see that? Well, let's look at the thing about the basis a little bit more carefully. Let's leave this up for the moment. So my basis states involve our familiar orbitals, excluding spin, tensored with the state having to do with the spin of the electron. These terms do not affect in any way the spin of the electron. They are motional operators, having to do with the momentum and position operators, having nothing to do with spin. So they certainly do not couple states with different m sub s values. Okay, so kinetic energy and Darwin do not affect the spin or affect. So the only thing that they could couple are states, well, they could couple states of different L in principle, and they could couple states of different m sub L in principle. However, they don't. How do we see that? These terms are also symmetric. So they clearly don't affect the m sub L values, because any rotationally symmetric potential, as we discussed earlier in the semester, can't couple states of different m sub L. That is a selection rule if you have rotational symmetry. So let's take a look at these terms a little bit more carefully. Let's look at this. Okay, all right, over here. So let's look at the matrix elements. So first, let's look at the kinetic energy term. So what do we have here? We're looking, if I look at the diagonal matrix element here, now, there's a trick that we can use to solve this without going through the hassle of generating functions, of radial equations, and the mess all that we did in one of the early problem sets. Because if we look at this, what we see is that this matrix element is the same thing as what I get when I look at the inner product of that with that. So I just broke up the p to the fourth as a p squared acting on the ket and a p squared acting on the bra. And that is the same thing as the norm squared of what happens when I operate the p squared operator on that ket. But p squared operating on this ket is something we can easily calculate, or at least we can calculate this norm because of the following. We know that p squared over 2m, or 2 in the case of writing this in atomic units, minus 1 over r acting on this, is an eigenstate. That's what defined these states, with eigenvalue given by the Rydberg, the usual expression for the bound states of hydrogen. Okay, so that means that p squared acting on this ket is the same thing as minus 1 over 2n squared plus 1 over r acting on this ket. So we see, first of all, since 1 over r also, it does not couple different L's. We can see that there won't be any off-diagonal matrix elements between different L's as well. But now we can calculate the norm of this vector, because the norm of this vector is just equal to the norm of minus 1 over 2n squared plus 1 over r and ml squared, which is equal to 1 over 4 n to the 4th minus 1 over n squared, the expectation value of that, plus the expectation value of 1 over r squared. If I did that right. Always a dangerous thing to do algebra on the board, but let's double check. Not that my notes are right either, but that's a different story. Looks good. All right. No, it's not right. I knew there was something wrong there. I forgot this factor of 2 when I solved for p squared. So it should have been 2 times that. Right, p squared. So, there is a factor of 2 here, factor of 2 in front of everything. So I guess that would be, I have to square it, so that's 4. All right, so we did this for homework. We calculated these matrix elements. I'm going to carry my notes around at this point because that's not going to be right if I don't do that. This itself is equal to 1 over n squared, and this is equal to 1 over n cubed L plus a half, which we got from the Feynman-Tillman theorem and all of that in the previous problem set. So, when we put all of that together, what we find is that the expectation value, the diagonal matrix elements of kinetic energy correction is equal to minus alpha squared over 2 times minus 3 over 4 n to the 4th plus 1 over n. Okay. So for n equals 2, equals to L equals 0. That is the 2s state. And for the 2p state, I got it somewhere. Oh, well, I'll come back to that because I don't have it separately. Let's just look at the 2s block for the moment. All right, so for 2s, we have this term. So our 2 by 2 block here, this of course is independent of spin. So this matrix element is the same for the two matrix element, the two entries in the 2s. We said this term does not contribute because L equals 0. And now we need to think about this term. The Darwin term. Let's take a look at that matrix element. Okay, just generally we'll have that those kind of matrices. Well, this depends on only the value of the wave function at the origin, right? And we know that the only wave functions that have non-zero value at the origin are the L equals 0, the S states. So this is only non-zero when L equals 0 and ML equals 0. There is no other matrix element. So this matrix element then is equal to the square of the amplitude of the wave function at the origin only for the S state. And in the that means that this term in the context for n equals 2 is given here somewhere. Gotta write it down. This, of course, is equal to the YLM is 1 over 4 pi times the value of the radial wave function at the origin. So let's see what that is. So this then is equal to this value for the 2s state is a half, so this becomes equal to alpha squared over 16 for 2s. Okay, so putting this all together, what we have is 2s doubly degenerate is shifted, and it's shifted by an energy in atomic units of minus 5/8 alpha squared. Okay, and if I put it back in atomic units, it's that, which is 27.2 electron volts. So this energy is equal to 56.6 micro EVs. Now, who the heck knows what that is? It's not a unit that perhaps we typically work with. There's lots of different units that one typically works with. If you look at traditional atomic physics spectroscopy, they work in something called wave numbers. What the heck is a wave number? Well, a wave number was the way spectrometers used to be calibrated in terms of inverse wavelengths. So they were units of centimeters to the -1, and often you'll see if you look at old spectroscopy books, they're often discussed in terms of wave numbers. Probably a more useful unit is to think about things in terms of frequencies, because spectrometers are now in terms of frequencies. So 1 gigahertz is about 4 micro eV. So this energy is approximately 13.8 gigahertz, which is a microwave frequency. Okay. All right, so the 2s state, we didn't break the degeneracy, we just shifted the energy down ISO amount. Now let's look at the,
So you still can't perform perturbation theory then on those levels?
what do you mean?
Well, they're still degenerate, so in the second order term, you still have the problem with the denominator. Once if you sum over,
Degenerate perturbation theory.
but well, they're still degenerate, right? So you haven't broken the
theory will never be broken, no matter how many orders of perturbation theory. We did not do first order perturbation theory. All we did in this case was we diagonalized this Hamiltonian, and we didn't. And that takes all orders of this. Now, of course, we can ask about coupling of other perturbations to the higher, but it's never going to break this degeneracy because as long as L is a good quantum number, when I have L equals 0, there's no spin orbit coupling. So this term is negligible, and this term does not in any way affect the m sub s values. So it will not break that degeneracy to all orders. Something has to couple in order to break that degeneracy. There will always be some degeneracy remaining, as we will see, because there are some remaining symmetries in the problem. Degeneracy and symmetry are intimately related. So as we'll see, the total angular momentum has to be conserved because there is overall conservation of angular momentum. It's just the individual orbital angular momentum and spin angular momentum aren't necessarily conserved. They can be mixed and coupled together as they are in this term. But if L equals 0, that doesn't do anything. So let's think now about the 2p block. Well, the 2p block is going to have firstly, we know, as when we just discussed, there's no off-diagonal elements of this kinetic energy term between different L. So there's no off-diagonal elements between 2s and 2p coupled by the kinetic energy. That's what we just discussed over here. Moreover, the 2p doesn't in any way affect, there's no Darwin correction to the 2p state because the p orbitals have 0 probability to be at the origin. So the only possible off-diagonal elements between 2p and 2s will be through spin orbit. We'll come back to that in a moment. So we can look at, first of all, there's the Darwin, or the kinetic energy plus Darwin corrections, which we just calculated. Well, this is 0 for 2p. There's this term, and it's sitting over here. And we could put it in for L equals 1. And what do we get? We get something. Come back to that in a moment. So we have our, these correspond to diagonal matrix elements. to this six by six matrix that we were discussing. Now we must consider the spin orbit coupling, because now L is not zero, so we have to think about that. So now we need to diagonalize spin orbit term. This correction, this is the same for every one of those 6 states in the 6 by 6 block. So we don't have to worry about this messing up the diagonalization, because this is just the identity matrix, right? So we need to diagonalize this, and this stays diagonal, and then just adds to whatever the eigenvalues we find here. We need to add this to every one of those terms. Okay? So we need to diagonalize this matrix. For that, we're going to do a little bit of a foray into a quick review of the addition of angular momentum. In 0th order, we were treating as our basis, without any of the relativistic corrections, in terms of the angular momentum, L m sub L and S m sub S. These were our good quantum numbers. And as you remember, these states, when we have 2 angular momenta, we have L, the orbital, and S, the spin. Okay? And in order to specify the states of the system, we have some choices in terms of a complete set of commuting operators. We have the so-called uncoupled basis, in which we have the simultaneous eigenvectors of L squared, LZ, S squared, and SZ. That's this basis. So these simultaneous eigenvectors we wrote as such. Product state, or the so-called coupled basis. And the coupled basis, we look at the total angular momentum, the sum of L and S, and traditionally in atomic physics, that's called J. So we have, as an alternative way of specifying the state, we can specify a different set of commuting operators. The magnitude of all of them, the magnitude of the total, the magnitude of the individual, and then the projection of the total on a particular axis, which we generally call the z-axis, right? And you know that these are incompatible sets because JZ does not commute with L squared or S squared, okay? And so we can write the coupled basis terms of these 4 quantum numbers instead of these 4 quantum numbers, where 2 of them are shared. The L and S quantum numbers are the same, but the 2 of the quantum numbers are different. And of course, you remember that if I have a particular for a given L and S, then J can take on values between L plus S and the magnitude of L minus S. This would be true, of course, no matter what 2 quantum numbers. I'm talking about just, I'm adding, let me say more generically. J is the sum of J1 plus J2, then J is between J1 plus J2 and J1 minus J2, whatever the magnitude of that is in interviews. So just to remind you, this picture we have of the addition of angular momentum, we often look in terms of a kind of vector sum, kind of classically. The uncoupled basis what we do is the following. We say we have some particular J1. Its magnitude is fixed and its projection along some quantization axis is fixed. So as a kind of classical vector, we say that the vector could be somewhere along this circle. We don't know where because the other components are completely uncertain, or uncertain to within some range. And then we have some there's a different size vector, J2, with its particular projection fixed along the axis. But the sum, the magnitude of the sum is not fixed, nor is the projection of the magnitude fixed, because I can add these 2 different circles in many different ways and have many different projections. So that's the uncoupled basis, where we think about, this is the basis which is, in some sense, space fixed, because I've specified a quantization axis and I've sort of pinned the projection of each of the angular momenta to some position in space. On the other hand, in the coupled basis is more body fixed. So in the coupled basis, what I think about is that I have a particular definite magnitude of the 2 angular momentum. I'm sorry, the magnitude of the sum is fixed. Also, the magnitude of the individuals are fixed. But the projections of the individuals are not fixed. What's instead fixed is let me draw this a little more cleanly. The projection of the magnitude. So I think it's a useful physical picture to think in this picture, the individual angular momenta vectors are processing around the sum of the 2. And then the sum of the 2 has some definite magnitude, but it It's the individual projections could be anything consistent with that sum. So in some sense, the coupled representation physically has to do with something when the two angular momenta are coupled together, and the forces that couple together sort of fix what they are, whereas the uncoupled basis is the appropriate basis when the coupling between them is weak, and in some sense they're more pinned to external forces that fix them in space. So as we will see, if we're thinking about, for example, a strong magnetic field and the Zeeman effect acting on atoms, the uncoupled basis is the appropriate good quantum numbers because the individual spins are processing around the space-fixed magnetic field rather around processing around each other. In the absence of a field, when the two angular momenta are coupled to one another, the coupled basis is the good basis.
So is there a continuous transform between the bases that's ever useful?
No, I mean, at the end of the day, we have to think about the set of mutual commuting operators. There's no kind of continuous distribution I think would be useful in this context. There are really these two bases in this context. Of course, there's, what you choose for the quantization axis could be, that is a continuum. But other than that, really no. So, but there is, of course, a way to transform between those because they're both bases. By the way, how many different vectors are there within a given coupled set? In this case, we have the total number of states. In this case, I have 2L plus 1 times 2S plus 1. Well, maybe, sorry, let me just write this over here relative to the more generic case. So if I fix J1 and J2, then the total on the uncoupled basis, I have 2J plus 1 times 2J plus 1 plus 2, right? Because each one of the individual angular momenta have 2J plus 1 projections, right? And the product of them is the total dimension of the space. In the coupled basis, well, J means that M sub J can go from this word capital, let me call that capital J, can go, the JZ eigenvalues, M sub J, can go from minus J to J, so 2J plus 1. And then J goes from to that. And of course, they have to be the same. It's the same subspace, just two different bases. So the dimension of the Hilbert space is the same, no matter what representation I'm using. It's just how I label those basis vectors and what they are. So I can do a change of basis. And if I have a one basis vector, I can express a basis vector in the coupled representation in terms of a superposition summed over M1, M2, and J equals sorry, I don't have enough room here. Let me rewrite it over here. Pardon me. Let's do a change of basis. We have the uncoupled basis, which for more simplistic notation, I will put them all together in one cat, where this is a shorthand for this product state. Okay? We have the coupled basis, in which we have these quantum numbers. And now we can do a change of basis. So if I start with the uncoupled basis, I can change to the coupled basis by putting in a complete set. And for a fixed little j, I have to sum here over j mj, and this equals j. Now, oh, that's why I got myself confused. Sorry. That's just pretty much what it said. I did it backwards the way I was wanting to do it. Of course, I can do the other change of basis, which is I can sum over M1, M2. Putting in a complete set of uncoupled basis states, right? So I just inserted the identity either on this state or on that state to do a change of basis. These coefficients, which correspond to the change of basis, you'll recall, are called Clebsch-Gordan coefficients. We'll talk just a moment about some of their properties, but let me quickly just say something about the notation. There's a jillion different notations that you'll see in every textbook about how you write Clebsch-Gordan coefficients. We're going to use a particular notation here. Because J1 and J2 are the same, they have to be, otherwise this is non-zero because we know they share the same, that the little j's are common eigenvalues. We often don't repeat them. So I will write this as J, M, J1, M1, J2, M2, without writing this a second time, because that's already kind of given, we know it's J1 and J2. The Clebsch-Gordan coefficients, they're important. They kind of show up everywhere in atomic physics, so let's review a few things about them. conversely, what we see is since the total J projection is the sum of the projections of the individual J's, we know that M has to equal M1 plus M2. That is, say, if I put the matrix element of JZ between the two basis elements, this is 0 unless M equals M1 plus M2. Therefore, the Clebsch-Gordon coefficient is 0 unless M1 equals M1 plus M2. So in fact, we don't have to sum over both M1 and M2 because the sum of them is constrained to be capital M. What else can we say? Well, we have what's called the triangle inequality. Which was related to the fact that the magnitude of J for the sum was between the difference in the sum. So the Clebsch-Gordon coefficients will be 0 unless J satisfies the fact that J1 plus J2 is no bigger than J and J1 minus J2 magnitude is no less than J. There are some other properties that have to do with conventions. They're phase conventions. One, the CG coefficients are real. So that means that, in fact, in these two different expressions, this is equal to its conjugate. Doesn't matter which order you're in, they're chosen to be real. Let me find the additional. We have a set of conventions here that if I switch the order of which I call 1 and which I call 2, there's a minus sign, which is minus 1 to the J1 plus J2 minus J. We have the rule that if I switch n to minus m and m1 to minus m1 and m2 to minus m2, this is equal to this same sign convention. And finally, if I switch and I say, instead of adding angular momentum, I'm going to subtract angular momentum, where, let's see, this has got to be a minus, m is equal to m1 plus m2. This is equal to minus 1 to the J2 plus M2 over the square root of times the usual CG, the one that's this guy. these conventions follow from the algebra of angular momentum SU2. And they're discussed, for example, in detail in Cohen-Tanucci Volume 2. If you look in Cohen-Tanucci Volume 2 on addition of angular momentum, they're all there, or any standard text that talks about the quantum mechanics of angular momentum, such as Edmonds or Rose or any of those. We'll give some reference to those for our notes. I never remember these conventions. Now, these conventions are ugly. And so one of the things that Wigner wanted to do when he really formalized the theory of angular momentum and quantum mechanics was get rid of all these signs. And so often in atomic physics, one, instead of using Clebsch-Gordon coefficients, we used a set of coefficients that Wigner introduced called the 3J coefficients. We rarely use them anymore because all our computers have some program in them that can calculate Clebsch-Gordon coefficients, and they don't have to worry about all the phase conventions. But if we want to, we could use the Wigner 3J symbol, and the Wigner 3J symbol is defined as following. Instead, so I have the 3 magnitudes up top, the 3 projections down below, and it's equal to -1.
Wait, so is the J on the bottom the big J?
It's the big MJ.
Oh, sorry, on the right side, under the square root? Is that the,
You know, it's a good question. It must be.
so that's,
In my notes, it looks like
Okay.
a little bit, but it must be that.
And the-
It must be
yeah.
that. I don't remember, but it must be. The point of the Wigner 3J symbols is that this is invariant under cyclic permutations of columns. So I can move them all around and it's the same, and all the signs are picked up by this. So for an example, if you use Mathematica, Mathematica calculates Clebsch-Gordon coefficients. That's how I get my Clebsch-Gordon coefficients. But if you put in the wrong thing, it says something like 3J symbol not allowed, because somehow Mathematica stores the 3J symbols, not the Clebsch-Gordon coefficients, and then uses that to calculate. So if you violate the triangle inequality, or it says this is bad. I mean, you know, some old version, maybe Mathematica 6.2, it would bomb if you. Now I think it gives you 0. But it used to say this. It would just give an error, say this is not an allowed bigger regions. All right. Everybody should go back and review their addition of angular momentum because it's essential in understanding atomic physics. Now we're going to use it. We still haven't finished the problem at hand, which was the fine structure. So we're going to finish that today, one way or the other, if we go to noon. What was the point of all of this? Well, the spin orbit coupling okay, we need to diagonalize this in the basis N, L, m sub l s m sub s. Right? These were our zeroth order basis vectors. We're writing a matrix representation of this observable in this basis. And then we wanted to diagonalize it. Of course, this is equal to the radial part times the YLM and then the spin, right? This was our usual orbital, and then we have spin. So our zeroth order eigenvectors are in the uncoupled basis. And we have to diagonalize this in that basis. What can we say about that? Well, we could express this in terms of Lx Sx plus Ly Sy plus Lz Sz, and then write that operator in this basis, and then diagonalize it. We could do that, but we would be fools. We're not fools. We know we can diagonalize this by I. Why? Because note, L dot S, well, note, if I look at the magnitude of the total angular momentum of the electron, spin plus orbital squared, that's L squared plus S squared. Of course, L and S commute, so I can write this as 2 L dot S. So, L dot S is another way of writing 1/2 J squared minus L squared minus S squared. So L dot S commutes with J squared because J squared commutes with this, J squared commutes with that, and J squared commutes with that. It commutes with L squared because L squared commutes with that, L squared commutes with that, and X commutes with S squared. Blah, 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 blah. However, what about JZ? Yeah, JZ commutes with this, and that's a mutually commuting set of observables. So the eigenvectors of L dot S are the coupled basis vectors. The vectors with good quantum numbers J, L, S, and Mj. And what are the eigenvalues? Well, the eigenvalue of J squared is JJ plus 1. The eigenvalue of L squared is LL plus 1. And the eigenvalue of S squared is SS plus 1, which of course is 3/4, because S is fixed at half. Remember, in atomic physics, S has two meanings simultaneously, as annoying as it gets. S can represent the spin of the electron quantum number, S equals 1/2, or I could be talking about an S state, which has to do with L equals 0. Who invented that notation? They should be shocked, but they're probably long dead, so it's too late for that. All right, so we also see from this little exercise that the spin-orbit coupling doesn't couple states of different L, because this commutes with L squared. So there are no off-diagonal elements between the 2s block and the 2p block. It was only, and the only off-diagonal elements are between the different m sub s and m sub l's within the 2p block. All right, let's put it all together. So new eigenvectors for 2p. They now have n, j, mj, l, and s as good quantum numbers. Which is really, we still have we didn't mix the different radial parts, but we mix the angular part together and I won't typically just, I'll write it like this because L is given here and S is a half always. Okay. So in order to find what the actual energies are, by the way, we often write these orbitals now, new orbitals, N, L, J. For example, we have for hydrogen, we have the 2s 1s orbital, and then we have the 2p orbital, and we can ask the question, what are the possible values of j in the 2p orbital? Well, we had L equals 1. S was a half. So the possible values of j are j equals 3 halves and j equals 1 half, right? This was for L equals 1 plus S is a half. And this is L equals 1 minus S equals a half. There are 2 and mj is plus or minus a half here. And here mj is plus minus 3 halves plus minus